very rare that I come on after a speaker and he steals a lot of my lines. If you're hoping I'm going to be anti-fission, then you're sadly mistaken. I'm going to be very much in tune, and indeed I can race through the early bit justifying why we do fusion research, because I think without actually mentioning fusion, Philip has covered that very well. The need in many countries for sources of energy, and what are you going to research to do that, and obviously that's what fusion is all about. I also feel rather humble coming after someone like Philip. I'm not even a doctor, let alone a professor, and my father was a retired civil servant from London. But be that as it may, I did study physics a long time ago at the University College Swansea. I did physics at Culham for 10 years before I switched doing it to talking about it. And I spent most of my life talking about it to A-level physics students in the UK, of which we have as many visits as we can do, and primary school students in the UK, which is the most fun audience. With all due respect to yourselves, absolutely the most fun audience of all to talk about what we do. I always start talking about fusion, assuming some of you know nothing or very little about it, and I'm sure some of you know a lot about it, talking about the sun. He says here, can someone tell me, just to warm us up, how hot the sun is? The middle, the edge is a few thousand degrees, but can anyone tell me how hot the middle is? Yeah. 10 to the, yeah, it's about 15 million degrees, but you're in the right ballpark. One of the major differences between, of which there are many, the differences between fusion and fission, which ultimately is the same physical mechanism making the two things release energy. But one of the big differences, you need to work very hard to make fusion work. If the sun wasn't 15 million degrees, in other words, if the hydrogen nuclei in the sun weren't moving very, very fast. Now, I'm not talking about the speed of light, thankfully, at the minute, but moving somewhere around 1% of the speed of light. If they weren't moving that fast, they wouldn't have enough energy to stick together. So fusion is, by definition, a big energy balance. You have to put a lot in to get an even lot more out. And that's really been one of our problems. And if you're saying to yourself, well, why have those fusion guys just not cracked it yet? And how come fission has been around, as Philip has said, since the 50s in the UK, where the very first reactor started? It is immensely more difficult to make fusion work. But the flip side is it has advantages even over fission as a potential energy source if we can make it work. And that, of course, is why we at Culham and with the European Jet Experiment are doing the research that we're doing. But just to indicate to you, it ain't very easy. I'm going to race through a lot of this because Philip has very well covered it, and I don't want any of my numbers to look different from his, which I don't think they do. Population of the world rising somewhere around 7 billion at the minute, possibly 12, 13 billion by the end of this century. Very difficult to tell, with an expectation that it will start to level off, and that's a lot to do with developing countries becoming developed and having less children per family, etc., etc. But what will drive with that is a demand for more and more energy. Now, this is, for what it's worth, gigatons of oil, showing you a very steep rise in world energy demand. And don't get hung up on electricity now, that is about a third of energy demand. This is transportation and infrastructure and streetlights and factories and whatnot. All of that has driven very high, a very big increase in demand over the last 50 or so years. And then, depending on whether you're a real pessimist or more of an optimist or somewhere in the middle, the demand is going to rise. Any Americans in the audience, just so are you sure? Okay, I always think A is the American model, which for any of you who've been in the US will know exactly what I mean, a very high push. It's not as simple as, of course, as saying more people is more energy. And these numbers are very difficult, and I know Philip once or twice said difficult to actually get the real numbers. When you're looking at energy, it's a rather difficult subject to get exact numbers for. But the way you tend to mark how much energy people are burning in different countries is in a year per person. You share out the total energy bill for that country, again, electricity, transport, everything. And you work it out in what they call tons of coal equivalent. Now, you could call this tons of oil or tons of gas. It's tons of fossil fuel. For someone, I'm dreadfully unpolitical now, so this should not say Western Europe, this should say most developed countries. Ireland and the UK would be in here somewhere where plus or minus a tonne or so, you're around 6 tonnes for every one of us in this room. So if we got all our fuel, and certainly in the UK, most of our electricity, virtually all our transportation is fossil fuel driven, then we're all around this number. The US is higher, and we won't go any more into that, it just is. The big scare, and Philip mentioned scaring several times, and it scares me a lot, is when you look at the numbers for countries like China and India, 1.3 billion people and just about 1 billion people. This number is almost certainly out of date already. As China develops so rapidly, 120 new nuclear power stations in the next 10 or 15 years, I think that's the plan. They will try and build, and rightly so in my opinion, but they are about a quarter of the level of us. But of course they're probably saying, well, why shouldn't we be here? Let's not hope they're aspiring to here. India, barely 10%. As the world develops, the drive for energy will be exacerbated. It's just not as simple as saying more people, more energy. It's more acute than that. So you then start to search for what you can do. Now, I won't say much more than this. I was very thankful that my oil production numbers were about right, because this was written 5 years ago, so I'm saying it's about peaking now. So that's certainly an agreement. Gas a little bit longer. Well, I'm 2020 and Philip said 2025. There's a bit more gas around. Very excited in the UK. There was not a big press story, but a press story the other day. They found a lot of shale gas in Lancashire. Big reserves, really significant reserves, but with a big rider that getting it out is extremely difficult. Could be a lot of chemical pumped into the ground to get the gas out. What are you going to do to the aquifers, the water table and everything? So it's not without its own problems, but maybe that will have to be looked at. And of course, global warming. So one way or another, you need to start think of things to do other than that. I won't say very much about my thoughts on renewables, but not because I'm following Philip and frightened of what he's going to say, but I would very much mirror what he says. We have the same issues where the government in the UK is pushing wind very, very heavily, but I really struggle to see it making a major contribution. Of course, in a country with many more people and much less space, and in places like Oxfordshire, certainly much less wind than you would have here in Ireland. We have in the county of Oxfordshire, and I don't know how many people live in Oxfordshire, somewhere up towards 1 million, I guess, we have 5 turbines. There are a few more planned. Any time around the city of Oxford, and some of you may have visited Oxford, beautiful city, the Dreaming Spires and all that. Anytime anyone wants to build anything in the way of a turbine around Oxford, everyone goes mad. The Oxford Preservation Society, you must not spoil the skyline of this magnificent city. And I can see that. I live 10 miles south of Oxford, near where I work at Culham, and Didcot Power Station, down the road, a big gas and coal burning power station, 3.5 gigawatt station, is there every morning when I pull the curtains. Every so often I wonder if it will not be there, but it is every morning. Whichever way you do energy, it's going to spoil the skyline. Didcot spoils the skyline for South Oxfordshire, whichever way you come in. But to replace Didcot with turbines and get the same maximum capacity out, you're looking at 3,500 turbines, certainly 2,000 turbines. So the space, the physical space that would take does not bear thinking about. So you need to do as much as you can. If my director was here, and I would very much mirror, not because he's my director, but I tend to agree with him anyway, he would advocate much more solar. Now, Philip didn't say too much about solar. The numbers for solar are much more striking. Enough energy falling on the Sahara for everyone in the world, easy. Except no one lives in the Sahara, and you then have to move the energy. There have been big-scale plans mooted for great mirror farms across the Sahara, ship the electricity into southern Europe. But again, the grid line investment that Philip mentioned briefly when he talked about wind and things would be huge. You'd need an enormous new infrastructure, hundreds of billions of euros to get the electricity in. But my view is there's probably more in this than there is in this. Hydro, where you can do it, but that's pretty much been exploited largely. I was lucky enough to visit New Zealand a few years ago for a big family holiday, and massive hydro schemes because the geography makes it happen with very few people again. So about half New Zealand's electricity comes through hydro. Again, no nuclear. And I'm not going to mention anything about fission, except to say that because I'm going to tell you fusion is 30 years away or so, I would advocate doing fission. I would advocate the UK doing more than replacing the 4 that are going off stream with another 4. I would advocate the UK doing much more and building 10 or 15 or 20. That's not looking likely at the minute. But I am pleased the UK has not, as in the case of Germany, shied right back from nuclear. It's much more as positive as it was about it, which isn't desperately positive, but it sees the need. And I would love, probably the only person in my village at the minute, but I would love to see our local power station not be a coal and gas burner but be a nuclear power station. That would be very good. If you said to me, of course, well, Chris, we're going to bury all the very high-level waste underneath your village, then maybe that would make me feel a little bit differently. It's not without its own issues, of course. But in the scheme of things, and when you look at the pros and cons of all of the options, I am very much in favour, and I would like to see another round around the world before hopefully fusion starts to come and ease the burden. And if my kids in 30 years were setting up home in a world where there was fission and fusion and renewables, then that would be the best I think I could hope for at the minute. And I'll tell you how we hope fusion will get there. I'm going to do a bit of physics, if that's all right, not a desperate amount, but I'm going to try and explain a little bit, obviously, the physics and the engineering and the politics and everything else of why fusion is good in about 25 minutes. So let's see how we get on. We don't actually do exactly what the sun does. The sun does, as I said earlier, hydrogen fusion, which, as you will know, is a single proton. And it's a very complex, it would take me the next half an hour if I understood it completely to explain exactly what process is going on in the sun. It's a multi-stage reaction. It goes through several stages with several fundamental particles coming in and out. And finally, the single hydrogen protons will stick together and neutrons get added in and they turn into helium and release some energy. The thing about the sun is it's pitifully slow. It's enormous, which makes it work incredibly well, but its reaction rate is pitifully slow. So if we said here on Earth, say 1,000 cubic metre sun, which is the kind of thing we'd be aiming at in a future power station, and we wanted to do exactly what the sun does, we would get nanowatts out. It would be completely useless and uncommercial. So we have to choose something that will react much quicker and that will give us a lot more energy out. And there are all sorts of reactions at the bottom end of the periodic table which will fuse together. And the one that jumps out at you as the most effective in many ways, although it has some drawbacks, is this one. So this is deuterium, a proton and a neutron, a heavy isotope of hydrogen, and tritium, 1 proton and 2 neutrons, a super heavy isotope of hydrogen. And if under the right conditions, and this is where your velocity or temperature comes in, you can speed them up enough so that they'll stick, they will irreversibly and permanently make this, helium, and 1 single extra neutron and a mass of energy coming out. Now, I hesitate to put that reaction up at the minute because the whole world seems to be wondering whether that's still exactly right. But of course, the reason you're releasing some energy is to do with the binding energy, the amount of energy a nucleus uses up to just hold it all in place, which is very, very significant, an enormous release from a very small amount of material. This reaction, compared to hydrogen-hydrogen fusion, is much, much faster. It's cross-section, if you like. The probability it will react if you have enough in your bottle of stuff and it's hot enough is much, much higher. To give you an idea, if the sun happened to have been made with deuterium and tritium in it, which luckily it wasn't, then it would have finished reacting in about a second after it started, compared to about 12 billion years worth of reaction. So you can see quite how much slower the sun is compared to what we're trying to do. And a good job, of course, otherwise it would have gone away very quickly. So this is all, again, tied up with E equals mc squared. If you work out that energy is mass, these two together, despite the fact that it's 5 particles just the same, weigh about 0.5% less than they did when they started. You have released, because this helium is held together so much more effectively than these, this needs less binding energy gets released. In terms of velocity, these come in very fast. So, as I said, 1% of the speed of light or so on average. They have a variety of velocities. And this comes out 5 times quicker, and this comes out about 30 times faster. 1,000 times more energy gets released here in terms of kinetic energy. So this neutron is the one you want to remember. That's the one we want to capture and turn into electricity one day. But this is the reaction that we want to get going, because it will give us gigawatts out. That won't be the problem. The problems lie elsewhere. Very quickly, and you will know all this, the binding energy here shows you why both fission down here, breaking apart very heavy nuclei, releases energy because it's making 2 things that need less binding energy, and indeed why fusion. And I was pleased actually because I didn't realise I got this spike on here. That spike is helium. Helium, that's one of the reasons deuterium tritium making helium gives us such an effective release, is that helium is particularly efficiently bound, so you get a large release of energy. fusion and fission. So the same fundamental reason why the thing happens, just looking at it from a different point of view. And as soon as you do start to look at it, you start to see why it's much more difficult. As we've already said, the sun, 15 million degrees. The simple fact is that if you just have a bottle of deuterium and you pour some tritium gas into your bottle of deuterium and you shake it, or you shine some light on it, or you play some music at it or whatever, it just won't do anything. Cold fusion advocate up here would tell you it would, but I'm going to tell you it doesn't. So you need to do something like the sun does, and that involves energizing it. And the reason you need such extreme temperatures, such extreme velocities, is the fact that very quickly when you take any neutral gas and heat it up beyond a few thousand degrees, it turns into this thing called plasma. We get emails sometimes at work asking what blood research we do. People watch Casualty, and the word plasma comes up. I hate Casualty, but that's not the point. The word plasma comes up and it was, oh, what blood work do you do? It doesn't happen very often, but we have had the odd one. This is ionized gas plasma, the fact that the electrons just aren't going to hang around on the atoms once you heat them up to very high energies. And this really exacerbates the problem. Now all of a sudden, forget the electrons, they're in there, but they don't really matter. You have positive nuclei spinning around, and the reason you need to get them up to millions of degrees is the fact that they just will repel each other. Unless you get them a nuclear width apart from each other, they won't pull in and stick. That's when the strong force will pull them in. Otherwise, they'll just bounce off. So it's brute force. Heat it so hot that they can't help but get close enough to stick. But how hot is 15 million degrees for the sun? It's of that order for most stars. Some are up in the 30, 40 million degrees. But because we're smaller, and because DT dictates it, we have to be up in the 150 to 200 million degrees. So challenge number one straight away is heat your gas to 150 to 200 million degrees before you can even start to consider seeing something come out. Now that's doable as long as you've got a very small amount of gas. If you have too much gas, it won't sustain itself and it won't ever get there. So you have to have a very small amount. But you can see instantly why this is much, much more difficult to try and tame than fission, which happens very easily. And you put the fuel in, 3.5 years worth of fuel, and you moderate and you carefully control the reaction, but it will give you energy without really trying very hard. Here you have to try very, very hard because of this thing called a plasma. I, for 10 years, and many of my colleagues at Culham are plasma physicists. They are studying how this thing behaves. Now, all of a sudden, as you will know and will have taught very much, gas laws are extremely simple to understand. You can macroscopically explain a gas with just a few very simple equations, the volume and the pressure and the density. All of a sudden now, every one of your particles in here has a charge. So there's a lot of force between the particles, some attractive, some repulsive. Every time one of them moves, it makes a magnetic field, which affects the charged one nearby, a little bit less. Trying to model and understand this stuff is incredibly hard. And in lots of ways, even with the smartest computers now that we're using, and we've benefited enormously from big computing power, theoretically, major elements of what this plasma does, we still don't really understand, and that's just a fact. We just can't model and understand some of its absolute fundamental behaviour. A lot we can, but a lot we can't. So it's a very difficult thing to control and to understand to any degree, but it's what we're left with doing. Now, of course, gravity does an immensely important job in the sun in holding it all together. It's still relatively unstable, and I'll hope to show you a movie in a minute, although the movie's bothering me that it won't load up, but we'll try showing you how unstable our plasma is as well. But even though gravity is pulling the whole sun into this lovely, lovely sphere, you still see enormous flares and sunspots and all sorts going on, and the sun is getting a lot more unstable over the next couple of years, peaking in 2013. But gravity does a very important job of holding it all in one place. Of course, plasmas are relatively common. This, for what it's worth, this is temperature and this is density. So the aurora is a very low temperature, very low density plasma, right up to the very high temperature kind of ones we're dealing with at JET, and the laser fusion guys are dealing with as well. Lightning bolt, all the lights above our heads are plasma. It's not something that's very well known out there in the wider world, but it is something people are very familiar with, even if they don't really know that they are, if you like. And every star you see in the sky at night. Now, this is the only equation I'll show, so you can kind of breathe a sigh of relief after this slide. But this is the fundamental one if you're trying to explain what fusion's all about in about half an hour. Deuterium and tritium coming in, making helium and a nucleus. What dictates, apart from the velocity, the temperature, what dictates that this will get anything out at all? Lawson was a very famous, he didn't actually work at Culham, he worked at Oxford University, but he put his head to fusion one day in the physics department at Oxford. This was back in the early 50s. And he came up with this criterion, which says that to make fusion happen, I need these three parameters to all be maximised. In other words, if one of them is lower, I have to compensate by increasing significantly one of the others. And the first two are reasonably obvious. First of all, I need as much density of particles as I can. The more I've got in there, the more likely they are to stick and the more I'm going to get out. That kind of makes sense. There is a pretty hard limit in the kind of devices we run on this density. That you cannot sustain and hold a plasma with the magnetic fields, which I'll explain in a minute, with a very, very high density. So there is a reasonable limit there, which is lower than atmospheric density by a long degree. Temperature, we've already spoken about. It's the energy of the particles. And the final one is the ability of the whole plasma to hold energy inside itself. As I'll show you in a minute, and as you see with the sun is losing energy, which we take up as heat and light, by radiating. Radiation is really bad for us because our energy comes out in neutrons. We want to minimize radiation because what radiation does from the surfaces of our plasma is lose energy and everything starts to slow down. And this characteristic time is the time it would take for the whole plasma to lose all its energy if you switched every input power source off. Okay? Now, this confinement time is and I've heard various numbers, but it's in the tens of thousands of years for the sun. So as and when the sun stops fusing and stops producing energy to keep it hot, how long will it take to cool down? Tens of thousands of years, and it will get big, and then it will get small, and it will finally fade away. Whenever we go and speak to primary schools, they're very disappointed our sun won't explode. They want it to be a supernova, and the really brave boys, notably, want it to be a supernova tonight. But typically the girls are absolutely petrified it will happen in 5 billion years' time. And I did get in trouble with that with a primary school audience the first time I did it, so I've not talked about it much since. That time for our plasma is about a second, simply because we're small. A small plasma has a lot of surface area. It radiates far too quickly for us. We minimise as hard as we possibly can the radiation by making it as pure as we can, but that number is small. And this really dictates why we fail on our own machines at the minute to get much more out than in, and why we need to go to big devices in the future. This is a very small number. So that's where we really work against. So we increase the temperature. Typically on jet, we have to get up to around 150, 200 million degrees, as I said, simply because this is so much less than the sun. That's one of the major reasons. We have to compensate, and we push the density as high as we can. The density in the sun is much higher as well. So to give you an idea on jet, we've got to about 110 to the 21 and made enormous progress over the decades to push up on that number. The only way we can get to exceed that is to increase this, which means you increase the size of the thing. Making a small fusion reactor does just not look possible for us to do. So we're looking at big gigawatt scale stations. But that is a bit of physics that explains the three things you really need to maximise. A little bit of science. Of course, as I've already mentioned, the fact that our particles are charged gives us one advantage. It gives us the ability with a magnetic field to haul them all in and control them. When we have A-level physics visits to Culham, I will start doing this to the kids. And I'll say, who knows about this? And the teachers then will go, oh, because half the kids look and say, oh yeah, I remember that from GCSE. It's all to do with the fact the particles are charged. The magnetic field influence, here are some field lines, means that the particles all of a sudden will have to orbit around the field lines. They have no choice. And if you make the field lines strong enough, the orbit is tight enough that you have a way of hauling the whole plasma in and controlling it. So we do magnetic confined fusion, magnetically controlled fusion, MCF what we call, the use of magnetic fields to sustain a plasma for relatively long periods of time and enable it to fuse. So that is one of the key bits of physics. When we have A-level physics visits, I will absolutely hammer this to them because I want them to come in and realise that an odd-looking place like Culham is doing for real what they're learning in the classroom. And you cannot sort of... that's just incomparable. I can go out and talk as much as I want, but when they go and see the stuff and realise what they're studying really works in the workplace, albeit an odd kind of workplace like Culham, then hopefully that will just turn a few of them round to realise this is all real and they might want to come and work with us. It's been around for a while. I'll show you very quickly some of the very early experiments. Oxford University, Imperial College, various places, and this is back in the 40s actually. Very small toroidal machines where you make a ring of plasma. That was very recognised very early on as being an attractive way of doing things, a plasma with no ends. And here is a good example of the instability. It would seem nice and happy with being pinched in off the walls with a bit of magnetic field. Then all of a sudden it would start to twist and turn like a snake. There are all sorts of ways that our plasmas want to get out of the field we're holding it in. And typically the hotter you make it, the more ways they'll find of trying to break free. So stability is a very, very difficult thing to fully understand and fully counter. And in some ways you can't. You have to live with some of it. Some of it you can mitigate and get rid of. But that's a good example of some of the kind of difficulties you face in the physics that we do. But you've rolled it all up into a machine that has kind of bobbed to the surface of all the designs that were out there in the 50s and the 60s. And in the early 60s, the machine called the Tokamak was developed in Russia originally. The Russians were very, very, and still are, extremely clever scientists and were well, not ahead, but certainly a little bit ahead of most other countries at the time. And this is a ring-shaped container surrounded by enormous electromagnetic coils. In the case of jet, these are huge coils of copper around which we feed enormous currents and voltages off the grid to make about 4 Tesla of field through the middle of the machine. And I'll show you the size in a second. So the magnetic field you're producing is doing as I've just showed you. It's like a big pair of hands. It's taking the plasma and it's just edging it away from the walls to enable it to get to hundreds of millions of degrees. If you allow the plasma to touch the walls, of course, it will cool very quickly and stop. Despite this magnetic field, if the plasma becomes so unstable it breaks out of the field and does hit the wall, all of a sudden about 1/100th of a gram of very, very hot stuff sees hundreds of tons of very, very cold wall, and it won't melt the whole thing. It just sees a very cold surface and it stops almost instantly. In a few milliseconds it's gone. Incredibly safe process. But of course, if you've got lots of kettles boiling in half time in the cup final, and all of a sudden you have a disruption, people aren't going to be very happy. So you have to master this, but deep down you know if anything's going to go wrong in the middle of a fusion reactor, it can't in any way go runaway or do anything to that degree, because you haven't got the fuel in there to make it. You put too much in, it will stop. Too little in, you make it too hot, too cold, too unstable. One way or another, it will hit the wall and it will self-protect every time. Okay? One way of heating, and there are many, is to feed an enormous current around the plasma. The plasma is a very good conductor. So you have a transformer winding down the middle, again about 1,000 turns on jet. There's only a few turns here. That essentially you change the current in here. It's a DC transformer, and you induce a current in one turn of plasma. And you drive around 5 million amps, incredibly good conductor, as I said. And that simply accelerates nuclei one way and electrons the other, and gets you up into the millions of degrees C. So when you strip it all back, it's a glorified transformer with some magnetic coils, which again is what we would really stress to the students, that the basis of all this is what they're doing at A level. And that's a really important message for us to get through to them, that this stuff they're working on really does work. This is the site we work at in Oxfordshire. Few of you I know have been before. There are 2 experiments that I'll tell you about in a second. JET is Europe's fusion experiment. We, Culham Centre for Fusion Energy, funded by the UK government, provide all the engineering support for JET. We're the sort of mechanics of it, if you like. We make sure it carries on running. We upgrade it when it needs upgrading. But it is exploited scientifically by Europe. So we would have as many as 150 maybe scientists from all over Europe, Ireland included, France and Spain and Italy and Germany, coming in task forces to run experiments that are very carefully coordinated and chosen towards the next machine. But it is Europe's device. So, it explains why it's still ahead of the world in terms of all other Tokamaks, because it has a lot more money behind it, being a European machine. We also have our own UK experiment called MAST, which I'll show you as well, which we're obviously very proud of, on a site that was an old airfield at the end of the Second World War. And you can kind of see the runway, which is there, no longer used for planes, of course. Would be much more fun if it was. So what about JET? JET is the Joint European Torus. It's been at Culham since 1983. That's a really appalling photograph, but it gives you some sense of the size of it. And a few of you I know have been and seen inside the doors. Here in front of you is one of the beam injectors. These are enormous accelerators that are accelerating beams of particles to send in and help heat the plasma up. Huge amount of engineering here as well. People often think from the outside, Culham is just a lab with lots of very clever scientists, which of course it is. But we have 60% of our staff are engineers. People have to build, maintain, upgrade all this equipment. And the scientists have nothing to play with if this doesn't work. And scientists typically, some are very good combinations of the two, but scientists typically aren't great at engineering stuff and vice versa. So the two have to work very closely. And our acute shortage actually of staff at the minute is really high quality trained engineers as opposed to scientists. That's where we're really struggling to find people. This is a better picture to give you some scale. JET is about 18 metres high. The vessel where you actually make the plasma with the magnetic coils around it is around 5 metres high, a couple of metres across. Just about 100 cubic metres of plasma you can make in there. Here is a standard European person to give you some scale. It is just about the biggest device. There's a device in Japan that's comparable, a little bit smaller. A couple in the US, notably D3D in San Diego, is about 2/3 of the size. A device in Germany about half the size. But throughout its over 25 years, almost 30-year life now, it's remained just about the biggest device around. There's the transformer winding down the middle, and these great orange limbs are the iron core for the transformer, and the return limbs for the iron core. So as I say, a lot of engineering as well as a lot of science. This is what it all looks like inside, all a bit space-agey looking. So obviously the plasma here we've shown, but it runs all the way round. We've just shown it one side so you can see an empty vessel. Now you have to kind of believe me here a bit, but I work in PR so you can. There's about a 5 centimetre gap. This is 2 metres, remember, this is 5. Here's where you can just about see the gap. Typically the edge kind of blooms up. The edge is very visible on a visible camera because it's about 10%, 5% of the core temperature. In the middle it's so hot here, 150, 200 million degrees typically, maybe even 250 million degrees if you're really doing well. You don't see any visible radiation, everything's burnt through. Lots of X-rays from here, but with a standard camera, which is what this is, you don't see anything. So it's a bit counterintuitive. It doesn't look like there's anything there, but there is. The edge is much cooler, so you do see it visibly because you get some charge exchange and some line radiation and things. But here you can see where the gap is. Typically, the gap is about 5 to 10 centimetres all the way round. And what you're doing, apart from at the bottom where you do let it touch, what you're doing is always monitoring what this plasma's doing. So if you suddenly see it moving up, you would very quickly, in microseconds, increase the field up here, push it back down again. So it's like a tiger in a cage. It's not a very politically correct thing to say now, but like a tiger in a cage with thousands of keepers around the cage that are saying, right, he's coming this way, poking back in the middle a bit. You're constantly working with the plasma to try and hold it where it is. It's almost a living thing, it feels like. And the hotter you get it, the more living it becomes. Of course, as I've already explained, very small amount of gas, 1/100 of a gram. So if it hits the wall, it's not going to melt it, but you don't build the wall of plasticine or something, of course. You build it with something that's tough. And up to now, carbon fibre has been the material of choice, and very, very good, very tough, robust, high melting point under thermal shock. In other words, if you increase its temperature rapidly, it doesn't crack or break apart very easily. So it's been this tiled kind of surface has been made out of carbon fibre. The bottom is where we let it touch and we release helium from the reaction. So this is particularly acute, the power loading down here. We have to get this right. The one big Achilles heel that carbon always has had that makes it unsuitable for a reactor, we've realised over the last few years, is its ability to retain tritium. In here you're going to have deuterium and tritium, and whether you like it or not, however much gap you've got here, there is some work, there's some transport of particles across. You don't want your wall to be like a sponge for tritium because one, tritium is incredibly expensive. It's a radioactive form of hydrogen, costs an awful lot of money, you don't want to store it in your walls. You want it to be reacting. We're going to make tritium in a power station. We don't want it stuck in the walls. And it makes the walls more radioactive than we'd like them to be. Fission, like fusion, is radioactive. People often say, well, it's so fantastic, there's no radioactivity. There is, because tritium is quite nasty stuff. Beta emitter, Philip was mentioning beta emitters earlier. 11-year half-life, you don't want it stuck in here, but carbon loves tritium. The atomic structure just sucks it in and holds it. So we've recognised we'd need to build the walls of something else. So for the last 2 years, which is why when Paul came, you went in to see the machine, because they were working on it, we've changed all the materials inside over. So every single tile has been taken off and replaced. And it was done with this robot. I'll show you the robot in a second. New diverter. Bottom diverter, we picked the toughest stuff we know, which is tungsten. So very, very difficult to erode or sputter tungsten at all. So that's what's at the bottom. Here, softer than carbon, but better at not sucking in tritium, is beryllium. So virtually all the inner and outer walls are beryllium. The other reason for that is you have to choose some kind of low Z material. You're going to get a bit of whatever this is in the plasma. If you put in a wall of iron, would be a disaster, because iron in the plasma would radiate like mad and the plasma would go out almost straight away. Low Z stuff loses its electrons quickly, doesn't cause you too many problems. So you have to look down the bottom end, and beryllium, softer, but the first results since we started plasmas back up have seemed very encouraging, that it's not sputtering too much beryllium into the plasma. Because it's radioactive in here to a degree, and we're talking about low levels, and we would very much understand a lot of what Philip said to you about the kind of levels you'd get on a jet plane, for instance, far outweigh what we would see anywhere near jet. But inside there is significant levels. We can send people in for about 2 weeks, and then they would receive their annual dose limit. Not a dangerous limit by any means, but that would be illegal for us to go on anymore. So we do have a few people that go in occasionally during one of these big shutdowns, but most of the time we work with the robot. Just checking the clock. And I'll show you the remote handling before I go back to that graph, actually. The robot works on a sort of mascot-slave principle. Here is somebody operating the robot arms, and whatever he does, the other end of it in the machine, 80 metres away or so, does exactly as he's telling it to the degree where if he's screwing a screw in with the end of the robot, as the screw gets tighter and tighter, he feels it tighter back here because the computer feedback tells him how tight it is. So crudely, he knows if he's going to strip a thread, which is what they're always worried about in here. You put different hands on depending on what you want to do. It actually is cleverer than human arms because the wrists turn through 360 degrees. You can try doing that with your wrist. If you can do it, then I'd like to meet you at coffee, because that would be a major achievement. This is laborious. It takes time, and we've been down, as I say, for 2 years to what seems like we'd just change a few tiles. It was over 4,000 tile changes one way or another. And you need to get it all right. It was a little bit delayed because there was more damage under some of the tiles than we'd expected. They use a fantastic virtual reality model. This is like an ultimate Wii game, where they show the robot arm coming in. They have, at any one point in real time, an exact knowledge of where they are, which seems trivial, but with TV screens, which they normally would use here, and cameras and TV screens, you get no depth of field perspective. This gives you everything you possibly want. This is an immense piece of software that they've developed. So it's spun out all sorts of other technologies, and there's a lot of interest in this kind of technology for future machines and other industries where remote handling is very important as well. I will just go back to that slide, which says that jet indeed has produced some fusion energy, but as many of you will know, not as much as you put in to heat it up. So this is power out against power in. Early experiments were doing nothing really until jet came along and really got going in the 90s, early 90s, and a device in the US that no longer runs called TFTR. These were both tritium compatible experiments. Jet's the only one in the world that can run with tritium. And jet has got up to getting about, the best was 16 megawatts of fusion power out, but you needed 23 megawatts in to heat the plasma to get you 16 out. 16 is not insignificant. That's a small town's worth or village's worth of electricity maybe, but you obviously would need to go up again. We will push tritium again in jet. We don't have much tritium at Culham. We don't like using it very much. One, because as I say, it's expensive and it's radioactive. So the last time we ran it was 96, actually 96 into 97 as it says there. 2014 we hope to go again, and I hope we get to, some people think we might get to Q of 2, will certainly exceed Q of 1. We're a little bit under at the minute, and we'll certainly just go a little bit over. But that isn't very clever for a power station. The key thing you can do is make it bigger and increase that confinement time number. That's the really important thing, because everything else has been maximised. But when people look back in 50 years at the annals of fusion history, jet will be hugely important, massively important as we've gone along the way. 5, yeah. So I've done that. Let me quickly show you MAST, and I'm going to zoom through those and show you a picture of the plasma. This is not a tritium machine. It's a much smaller, more compact, squeezed-in plasma, mega-amp spherical tokamak. We couldn't call it mega-amp almost spherical tokamak because that made a stupid name. So it's not quite spherical, but it's almost. And this is a bit of a clever idea we've come up with and a lab in the US at Princeton to say what happens if you squeeze everything in. Ultimately, you need less magnetic field, and that makes a big difference if you squash the whole thing in. Now, the key thing, this isn't as hot as jet. We're normally up to 20, 30 million degrees, okay, so it's a bit hotter than I've said there. The key thing for the whole talk is if this next bit works. Because if this doesn't, this will appear, and it isn't looking like it's going to. You just got to be a bit patient with me, because there's a very big movie I've loaded up, because I wanted you to see a plasma running. This is your worst nightmare. You never worry about questions. Give it ha, 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 ha. You see? Right, fantastic. Can you drop the lights, Paul? Can somebody... Sorry if that upsets the film crew, but that will be fine. As long as if you could drop those, that would be fantastic. But don't worry. This is a high-speed camera image of a Mars plasma. For those with very good eyesight, down here is the shot number and the time. This is time in milliseconds, so we've only gone through to about 200 and something milliseconds out of about 400. What you see, and it will run round again in a second, is you've created with the magnetic fields this nice circular edge, and you've separated the inner edge of the plasma from this solid column down the middle. That's what the magnetic field needs to do. This is neutral gas going in. What you see in terms of its stability is it seems very happy there. Then that is interspersed every 20 milliseconds or so. Energy is building up in there so much that it suddenly can't help but release it. And it flings it all out in a massive kind of explosion of energy out the edge, which people have likened. The energy equivalent onto the walls is like throwing a hand grenade at them, because you're throwing out so much so rapidly. It's a very difficult thing. It's one of these instabilities we can't actually get rid of, and we're going to have to live with if we can slow it and mitigate it as much as we can. But it shows you this sort of alive aspect. This isn't alive, of course, but it feels like it is, and you're working against this desire for it not to be stuck in here. I, like some of you, have primary school children at home, and it reminds me a little bit of my kids that seem very calm and settled one minute, and I've got 3 boys, and then will fly into a tantrum very readily the next. Maybe that's just me being a bad dad, but it's like the potential's building up, and then it can't help but just explode out. So that gives you an idea of the kind of issues physics-wise you're dealing with. Very, very quickly, I told you about solar flares. We see that kind of thing on the edge of our plasmas, and we've written Nature papers saying what the differences and similarities are between what the sun does and what we do. So it's a much more fluid process than fission, which kind of sits there and goes. Here you're battling against lots of different things. What can you do towards a future machine? We can't make jet hotter or denser because we've maximised those pretty much. The only thing you can do is go bigger. Bigger plasma, and this is ITER, 45 metres or so high and about the same across. A 12 metre high plasma chamber and about 5 metres rather than 5 and 2. So about 2 and a bit times bigger in every direction, 10 times the volume of plasma in here. So never mind 100 cubic metres, about 800 or 900 cubic metres. That means the plasma doesn't lose energy very quickly. That confinement time isn't a second anymore, it's about 5 to 7 seconds. That makes a massive difference. That means the energy you put in stays in long enough for everything to whiz round and fuse before it starts to get lost. At the minute, we're not kind of at the point where fusion takes over heating itself, if you like. This will do that. This will comfortably, and we're very confident of this, produce you 500 to 700 megawatts out. And what you'll do, rather than use copper coils, which consume a lot of electricity, it will have superconducting coils of niobium tin that will give you magnetic field essentially for free once they're up and running. To make you think of some of the engineering challenges here, 150 to 200 million degrees C, 4 degrees Kelvin out here for the magnetic coils to keep them super cool. So an enormous effort in engineering integration, bringing all the technologies together. A lot of it's been tested. The coils have been tested. Incidentally, you can't allow the neutrons here to get out to these very delicate coils because they'll break them very quickly. They'll quench them very rapidly. So enormous amount of thought has gone into the design of this machine. This is the International Tokamak Experimental Reactor. I have about 2 minutes, so I'll whiz through this quickly. The countries all along the bottom, Europe, in addition to China, Russia, Japan, the US, South Korea and India. Everyone thinks the US are pushing hard because they push hard on everything. They are not the prominent partner here. Japan, even now after Fukushima, has still put much more into fusion than most other countries. China doing an awful lot because as well as fission, they see fusion as a real answer in the long term. And Europe, those are the really three big players, with South Korea getting more interested and India. So it's a lot of effort. It's a lot of money to build this device, which is still an experiment, but which will answer all the questions to allow, and Philip's already talked about Westinghouse or EDF or somebody to start designing a fusion power station. No one will do it now because it's not certain we know how to do it properly and economically. But this is going to answer everything that we need to do. But we've chosen the site in Europe, which means Europe pays half that. That's not trivial at the minute, trust me, to get money out of Europe to that kind of level over the next 10 years. The operation is in late 2019. For those cynics amongst you, of which there are many, and I feel myself the same way sometimes, fusion is going to take a long time to get here. And people 10 years ago would have told you 30 years, and I'm still going to tell you 30 years. And sometimes I think, hold on a minute, what's happened? We've made a lot of progress, but sometimes you find problems as well as solutions. This will be the key. And if they can stick to this and get it running in the early 2020s, get results by the late 2020s for the first demonstrator, then we could have one in the mid-2030s. But the reason I say you need fission in the meantime is fusion isn't going to happen tomorrow. But in the absence of anything else, in terms of big energy research, there isn't much else, then you've got to go with this, because this could be enormously beneficial. Just to prove to you something's happening, that is a picture of the site. This is about 60 football pitches worth on the edge of the Cadarche site, which is an existing fission site. These are great big earth movers here, just to give you an idea. So it's a major undertaking. This is putting some of the concrete down to start the piles going in. Power plant, the one thing I'm going to mention very quickly is this blanket. We haven't tested a blanket on yet. Somehow you need to turn the energy of those neutrons into power, into electricity. So you need to turn them into heat. So you allow them to move into a blanket of lithium. The lithium does two things. As the neutrons penetrate in, they hit the lithium atoms and they slow and they slow and they slow and they heat the blanket up about 300 or 400 degrees, like a thermal cycle of any typical power station. And then you just have a steam turbine down here, just the same as anything else. But it has to do a second thing, this blanket. It has to turn the neutron into tritium, because tritium is very rare of the two fuels. Deuterium is very common, but tritium is very rare. So the reason you choose it of lithium is that lithium reacts with tritium to make helium and tritium. Lithium reacts with a neutron to make helium and tritium. And the tritium you release from the blanket, you have to feed back in. And you have to ensure you make as much tritium. You make tritium from every single neutron, so there's some multiplication in there as well. But that is the reason you choose lithium. So your fuels are actually lithium and deuterium from water and from land reserves of lithium. I've lost the last slide. What's gone wrong? Well, I can tell you the last slide because I know what it says. The advantages of fusion are enormous, but the disadvantage, of course, is that it's not working now. And if the world had taken fusion seriously when JET first came along, you could have easily had a speaker from ITER, might not have been me, saying how ITER's running. Politically, it's been an enormous challenge to get people to believe, to fund this. There's been faults in our own area as well, amongst the scientists as well. But nevertheless, it has enormous attractions. The energy, the fuels are enormously abundant. Deuterium, you're going to drink in a minute, and I will in a second, because there's 1 in 8,000 of every water molecule is deuterium. There is enough for billions and billions of years. Philip said something about a fission power station needing 20 tons a year. fusion power station would get by with somewhere between 0.5 ton and 1 ton of material a year, gigawatt power station. Now that is significantly less than 1 million times less than the amount of fossil fuel you need in a coal burner. Like Didcot down the road from me, train after train goes through every day to fill it up with coal. So you're getting a huge amount of energy from not much material. Some radioactivity from the tritium, from the neutrons being absorbed in the structure, but nothing that's going to last for more than 50 or 60 years. So no long-term legacy at all. And incredibly safe, because if it upsets itself, it hits the wall and stops. It's almost without compare. Holy grail. He has stolen my phrase, but it is. Except, of course, and maybe that's just the way of it, it's incredibly hard. So the engineering and the science is incredibly hard. Thanks very much for listening. I'm obviously around coffee, and I'll try and hang around for lunch because I don't fly out until later on today. If there's any questions, that's probably the time to do it. Thanks very much.